Good morning, everyone. Welcome to the workshop, Efficient Use of Nutrients and Water in Agriculture, Remote Sensing Data and Web GIS Platforms that is organized by the B-FERST project and also by ICONS and AgriSat. Next, okay. Before starting, I would like to remind to keep your microphones and cameras switched off. Use the chat box to pose your questions, and that the webinar is being recorded. Here you can see the workshop program. First of all, we'll start with a previous presentation of the B-FERST project, and after that, we will go with the first part of the workshop, that is with the presentation that will be conducted by Vicente Bodas, our agronomic director. That is called a time series of multispectral images for the agronomic management of crops. The objective of this presentation is to show the technical basis and the multiple practical applications of the use of remote sensing and web GIS in crop management. The second part will be the agronomic applications of remote sensing. This part is divided in three short presentations. The first one is the precise determination of water needs, of water requirements 1 week in advance. The determination of intra-plot variability and its application in precision agriculture, and the monitoring and management of nitrogenous nutrition by remote sensing. The objective of this part is to develop the lines of practical application of remote sensing information in agricultural work related to the use of water and nutrients. And finally, we will end this workshop with a practical application of remote sensing and web GIS, what we are doing, how we use these technologies in the project, in the first project. So the objective of this presentation is to show a practical application of remote sensing and web GIS related with to the field trials and the new fertilizers trials in the framework of this project. Okay. So now we are going to start with this previous presentation, that is the presentation of B-FERST project. Sorry. B-FERST project the name of this project is Bio-Based Fertilizing Products as the Best Practice for Agriculture Management Sustainability. This project have received funding from the European Union's Horizon 2020 Research and Innovation Program, and is a collaboration with the PBI and the Bio-Based Industries Consortium. So, B-FERST is a 5-year project which aims at creating new value chains by integrating the valorization of bio-wastes in the agriculture management. As main result, B-FERST will develop 8 new enhanced bio-based fertilizers by urban and agri-food wastes. And in the framework of circular economy and green chemistry, B-FERST will introduce an innovative model of sustainable agriculture production through a new generation of biofertilizers. The main objectives of the project are to obtain 8 new enhanced bio-based fertilizers, a new logistic model to use bio-waste at local and national and European Union level. 5 agricultural demo sites to validate the product, just to do a full market analysis, and to do communication and dissemination to introduce the products to the market. The specific objectives are to develop a logistic model to use bio-wastes for fertilizers production, to develop a new technology able to integrate low-cost primary resources from bio-wastes to the NPK production, to develop new biostimulants to improve fertilizers, to develop new mineral and organomineral fertilizers, and to prove new fertilizers effectiveness at demo level, with demo plants in Spain, Italy, France, Poland, and I want to highlight that Ukraine was included in this demo plants, demonstration trials, and due to the war in Ukraine, we have to move to another pilot zone, unfortunately. And the last specific objective is related with this workshop, that is to validate satellite images technology to monitor the experiments in the field. Here you are at Advanced Fertilizers Production scheme, where you can see that there are several sources for bio-waste and to obtain nutrient recovery. Also, we mix it with conventional natural or raw materials and with the use of biostimulants and coating agents in order to obtain these new fertilizers that will be advanced mineral and also organomineral fertilizers. And finally, I want to present the team, the partners involved in this project, that are Fertiberia from Spain as coordinator, University of León, also from Spain, Novamont from Italy, Aqualia from Spain, FCUR from Germany, and Agrisat from Spain. Agfutura, Vito, Arcadia, Icons, and Yum. Here you can see the nationalities of each partner. And that's all. I have finished this preliminary presentation. I want to introduce myself. I'm Andrés Cuesta, I'm agronomist. I work in Agrisat, and I'd like to introduce the rest of the presenters that are Vicente Bodas. I have told you about him. He's our agronomic director. And also Maria Calera, that she is the responsible of the management zone maps and the FertiMap service in Agrisat. So I'm going to go on with the first presentation. Now, Vicente, it's your turn.
Okay, thank you, Andrés. Okay, good morning. I have been an agronomist consultant for more than 30 years. And the first I have to say is I am not a technology enthusiast. I appreciate technology not for itself, no, because it's a new fashion. I appreciate technology only to the extent that it helps in my work. So I have a very practical approach about the technology. and this is what I want to share with you in this presentation. So I try to answer two simple questions. The first is why use remote sensing in agronomic management. I can give you for three answers, three reasons for using remote sensing. Quite obvious, but very powerful. First one is that remote sensing provides us an aerial perspective, and the aerial perspective is a powerful tool because we have a comprehensive view of the not only of the one field or one plot. We have a broad view of all the of an area, a region, and even a country. That is in this way it's easy to check the state of the crops and to see without being in the field. The second reason, and this is also very important, is that the cameras, the sensor of the remote sensing use another wavelengths different from the human vision, and in this way we have another way to see the reality, to perceive the growth in a different manner than in our own vision. And the third reason, and this very for me is one of the most important, is because all the information can be stored, managed, and shared in a standard way. If you have experience in the field, when you visit a field to inspect the growth, much of the information you receive come from your experience, your intuition. No for applying data collection methodology. Nobody go to instrument to visit a farmer to check the growth. Due to this limitation, it can therefore be said that this information you perceive is personal. It's impossible to share with another technician or with the farmer. So with remote sensing, everyone can see the same thing, have exactly the same information to assess the state of the crop, even without ever having been in that field. So this is a standard way to evaluate and to share the information. For me, this is crucial. Okay. The other big question is how help remote sensing to agronomic management. And what I can say is that remote sensing help in three basic needs that any farmer or any agronomist has when go to the field. These needs are to observe, to quantify, and to decide. A farmer or agronomist with experience when visit a field do these three things simultaneously, but it's very useful to separate them from the analysis. First, when we say observing, viewing, monitoring a crop, we go to the field to inspect the growth also, but how many times is necessary to go to the field to inspect a crop, any crop? You have to take into account that the crops are processes. It's not a stable thing. The crop are processes. So as much you visit the field, better. But it's impossible because it's very expensive and very time demanding. But we need to know what happens in the field every day, because every day in this process is important, because every day the crop are working, are photosynthesis, or so the only way to have a compressed information about how the crop is performing every day is the time series of image. You know, the time series of image provide us with a vision of any field, of any point in the field, without having been there. You know? One of the keys of using this technology, the remote sensing, is to have access in a simple way without a specific knowledge of GIS or remote sensing. So the system of platform like this of AgriSat is crucial, because people without any knowledge is able to understand how the image and how the crop develop along the time. Yeah. For people with some experience, the observation of this image provide a warning about the growth and development of the crop, and this warning it can be incident that often require further field investigation, but already targeted at the specific areas. This is a clear example. This is a seeding problem detected in the image, and when you go to the field, you realize that you cannot do anything, but you can take into account to further decision like fertilization rate or try to solve the problem with the seeding machine for the next season. After seeing the crops, observing the crops, we need to evaluate, to quantify, to measure. This is something impossible to do in the real life and in a routine visit to the field. But remote sensing provides us with different parameters like the vegetation index. Vegetation index, one of the most used vegetation index is this NDVI, normalized different vegetation index, that is calculated with this formula. It's not necessary to know the formula and all the knowledge behind this, but it's interesting to know that this index is able to represent the capacity of the crop to make photosynthesis. So thanks to this information, we can measure in every point of a plot, in every point of a field, how the crop is working. No? So we can see the crop in two ways. In this way, as you see in the real life, this is an example with a winter cereal, but we can see the crop with a curve. This curve is the evolution of the NDVI along the growing season, and this curve is an objective measure of what is happening. We can complement this curve with different milestones, and in this way we transform this curve in an excellent tool for benchmarking the crop. So we can evaluate the crop with objective figure, not with our impression, with our experience. Obviously, this kind of curve can be complemented with a lot of information. For instance, here you are it's for a winter cereal, high production winter cereal. We can complement with another information, like in this case, nitrogen uptake or biomass, dry matter biomass production. We can use to plan fertilization, to monitor the crop, to forecast final production, and to fix different targets in the management of the crop in every month. You know, this is another example in another different crop. This is spring garlic. That is to show that each crop has its own standard NDVI curve. And this curve is different for each crop and for each different agroecological zone. These curves are often called spectral footprint of the crop, and it's interesting for not only for agronomic management, also to different and classify the crops in an area. This kind of information is also useful in woody crops, not only in annual row crops. In woody crops, this is an example with almond, orchard with a high canopy, with a big canopy, and another with the canopy, a young orchard with a less canopy. And you can see the different evolution of the curve. Again, I want to insist that to be able to use this information is necessary to have a platform that allows direct access and inquiry of the curve to manage the information in a very simple way. And finally, observing, evaluating the growth, is necessary to decide to solve problem or to take action. Many often, thanks to the compressing information provided by remote sensing, you can make the most difficult decision for a consultant. That this most difficult decision is to do nothing. And when you decide to do nothing, is because you are very sure that the crop is evolving properly. So, without this global information provided by the image, only visiting a field is very difficult to have to be sure that this impression. Other time is necessary to do different things, like irrigate or to apply fertilizer or control pests and diseases. And in this sense, some derivative products are very useful, like the ones that my colleagues from AgriSat are going to present. For instance, Irrimax product that is served to calculate the groundwater requirements, and the Fertimax that is a service based on the characterization of the different productivity zone in a plot, in a parcel. Okay, this is thank you for your attention. This is my brief impression about the use of technology in the crop management.
Thank you very much, Vicente. Now we are going to start with the second part of the workshop, and in this case, the presentation about how we obtain the water needs, water requirements 1 week in advance using remote sensing. Okay. First, we will present the methodological principles. The basis of the methodology is FAO 56, in which the water requirements of a crop depend on the evaporative demand of the atmosphere, expressed by the reference evapotranspiration, or ETO, and the crop and its state, expressed by the crop coefficient, or KC. Reference evapotranspiration, ETO, depends on temperature, humidity, radiation, and wind. At AgriSat, we have access to ETO forecast information accumulated for the next week, spatialized and at a global scale. The crop coefficient evolves throughout the cycle of a crop. Its operational determination has been taking the phenological state as a reference, although it is really linked to the fraction of green vegetation cover. The problem with using phenology as a reference is that it doesn't take into account the size of the crop, which can vary its green vegetation cover. There is a linear relationship between the crop coefficient and the NDVI, since the latter is linearly related to the fraction of green vegetation cover. Each crop has a standard evolution curve of crop coefficient and therefore of NDVI. The relationship between basal crop coefficient and NDVI is universal, regardless of crop and location, not so far that of the simplified crop coefficient. For drip irrigation, irrigated woody crops, the KCB NDVI relationship can be used. Regarding herbaceous crops, this can be grouped into high coverage crops, maximum greater than 80%, in example, cereals, corn, alfalfa, and low coverage, in example, onion, garlics, and etc. The advantage of using the crop coefficient NDVI relationship is that it allows you to customize the estimates. In this example, we see that the same crop and variety can have different NDVI and therefore crop coefficient in different areas, whether they are from the same plot or between plots. From the NDVI value, and depending on the irrigation management unit or sector, we can obtain estimations of water requirements 1 week in advance. This calculation is the basis of our IRRIMAP service, in which we weekly inform the farmer of the water requirements of each crop in each irrigation sector. These requirements are not irrigation water, but they are a reference of the needs of the crop from which the farmer is able to make a weekly irrigation schedule. In this way, the farmer doesn't have to enter any data into the system. The accuracy of the estimate or prediction is very high and depends mainly on the accuracy of the weather forecast. We have incorporated into this survey the study of the evolution or temporal evolution of the spatial variability. This has allowed us to offer a high precision service to offer estimates of variable irrigation dose in pivots. We also offer in our service the possibility of estimating water requirements for controlled deficit irrigation. For example, in search of quality in high-value crops or for those farms that do not have large volumes of irrigation water. Just adapting the stress coefficient to the stage of the crop. Thanks to the fact that the NDVI evolution curve allows us to know the stage of the crop. The temporal evolution of the NDVI also allows to characterize the structural differences of the binder in this example. Here are different type of binders. As in the case of binder, we can also define different stress management strategies, as in the case of the almond tree and also in the olive tree. From a practical point of view, here we have an example of calculating water requirements in a binder with controlled deficit irrigation. You can see here that this is the equation that relates the NDVI with the basal crop coefficient, and it allows to obtain the transpiration, in this case the maximum transpiration, because we are not applying the crop stress coefficient, but we can multiply this maximum transpiration depending on the phenological state by the corresponding stress coefficient. A different state of vegetation represented by the NDVI will give us a different estimation of crop water requirements. Satellite observation of crops allows us to better manage the monitor the irrigation. For example, detecting deficiencies in the operation of an irrigation installation, as we can see in this example, where we can see that there was a problem in the final tower, the end tower of this pivot, and this problem remains and give us a different yield that in the rest of the part of the rest of the plot. Or rule out other causes that have nothing to do with poor management of the irrigation installation. In this case, the problem was that there was a human problem that working with the program of the irrigation. To determine the end date of irrigation, we have checked the satellite information with the use of capacity probes installed in plots, different plots, and we have observed what is the NDVI value when the crop doesn't need enough water, because it has enough water in the soil. So we can correlate this NDVI value with this moment and to know where is able to end the irrigation for the season. Although sometimes its implementation is not so simple, depending on the part of this value has remained. As mentioned, all this is part of our IRRI-MAPS service, of which you can find more information on the specific website. and in each you will find more reasons to use this service. Thank you for your attention, and now it's the turn for Maria.
Good morning. My name is Maria Calera. I'm working in AgriSat as the responsible of management zone maps or FERTI map service. Today, I'm going to tell you how we work in an operative way, because what is what we do. We work with farmers and we want them to have these services. So I'm gonna explain the first how we make the determination of the intraplot variability or the management zone maps. And as my colleagues have been saying, Vicente and Andres, we have a lot of information with the time series of NDVI, and we can capture in every stage or phenological stage of the crop the variability within the plot or within the field. So if we see here, we have 3 different curves of NDVI in the same field. So in order to generate a management zone map, what we do is an integration of the trajectory of each pixel within the paddock. And this enables us to pick up the variability, but pick up the variability, the accumulated variability along this growing cycle. So finally, we are detecting in all phases the variability of the crop. So in this case, for example, we have here the red curve, which is always above the green one or the blue one. So in this case, the red curve, it's gonna have more biomass than the blue one or the green one. How do we do this? With models. This is all modelized with NDVI, the relationships between NDVI, KC, crop coefficient, biomass, and the meteorology of the area. So finally, we get this kind of maps. What we do? This is a relative potential productive map. This is a management zone map. What we are seeing here, it's these areas of the plot, the brown areas of the plot are over the average. They are producing 10% more over the average. The yellow one parts are the parts of the plot that they are producing the average, and the purple ones are the less productive areas. This is very similar to a yield monitor map that you can create with the combine, but with the advantage of we have a repository of time series of NDVI of the previous years. So we don't need to have a combine with all the equipment and wait to the harvest to get the map. We can go to the past and make these kind of maps the previous years. And what can we do with these maps? In AgriSat, our most what we do with these maps mostly is fertilization, variable rate fertilization. So I'm going to present you a commercial case now. This is a plot from Albacete, where we are located. This is a rain-fed barley crop from the year 2019. This is a really big, it's big per plot, 100 hectares, and the target yield here in this area is 2,000 kilos per hectare. So here, for this 2,000 kilos per hectare, we apply here the strategy of fertilization here is one in pre-sowing application or sowing application and one in top dressing application. So the farmer made a blanket or homogeneous doses in the pre-sowing application, and we wanted to make a top dressing application in variable rate. So what we do first, we go to the past and make a multi-annual analysis of the plot. So if you see here, we have 4 years with different crops of the same plot. Finally, we need to select one of these to make the zones. So we talk to the farmer and say, okay, we have this kind of maps. We see here a pattern. It's very, very similar one year after the other, but we need to decide for one. And talking to the farmer, finally we decided to go with the 2017 map because the wheat has some experiments in this year. So once we have decided the map, we need to know things about the farm. If we work with a spreader, which is very, very new as this one, we could make many ranges, like the MCM or management zone map, or if we work with some different machinery that they are a little bit older or something that it's or maybe the work wide is very high, we can go to the simplified management zone map and go for 3 zones. It's more it's more usual to make these 3 zones map, but in some occasion we do this kind of maps too. Once we have defined the zones, we need to know which fertilization strategy we are going to follow. In these cases, this is a simplified approach, but what we say to our farmers is what we want: improving yield while maintaining costs, or reducing cost without decreasing yield. So what we do in the first case is we are going to apply the farmers' usual rate in the average areas, in medium areas. We are going to apply more in the areas that we are expecting more yield, and we are applying less in the areas that we are expecting less yield. The areas that the low areas, or the areas that we are expecting less yield, we assume that these areas are not gonna respond to the increase of the mineral fertilizer nitrogen, because if every year that we have been applying the same in an homogeneous rate, these areas haven't had any response to this homogeneous rate, or they are producing less, we think that the limiting factor is not the nitrogen, the mineral nitrogen. Maybe it could be another kind of problems, but not the mineral fertilization. In the other part, in the right part of the slide, we can see the other strategy. In these cases, the farmer want to reduce costs, and we can apply the farmers' usual rate in the areas that they are producing more, the high areas, the high productivity areas, and we are going to reduce the doses accordingly to the map in the other areas. And once we have decided all these things, we need to create the maps in the specific format of each terminal. This could be seen like an easy step, but what we have found here in Spain and in other countries, as Australia, that we are working with farmers there too in another European project, is that it's not that easy, because every supplier has different formats, and you need to you need to know how works these specific brands. So we work with our farmers too in order to move into the terminals and to get the variable rate done with success. You can see here more. This is our. You can see, you can find here more information about Fertimap service, and here other reasons or other utilities with the management zone map that I didn't say, but we have the management zone map could be used for more than this. But today I think it's enough. I'm Maria Calera, and you can reach me here.
Thank you, Maria. Now we're going to finish the second part with the presentation of called Monitoring and Management of Nitrogenous Nutrition by Remote Sensing, that will be conducted by Vicente Bodas. It's your turn.
Hello again. Regarding this subject, the management of nitrogen, in this presentation, I try to follow the same scheme that in my previous presentation. I try to answer two different questions. The first question is why use remote sensing to manage nitrogen fertilization. So the answer is very simple. The remote sensing allows us to use agronomic knowledge or scientific knowledge developed many years ago. This is an example. Here you are this parameter or this index, nitrogen nutrition index, that was developed in the 90s of the last century, more than 30 years ago. This index is the dream of any farmer or any agronomist, because allow to a continuous monitoring of the nitrogen status of a crop. Here you have a curve that represents the reference level of the nitrogen, the concentration in the tissues of the crop. And this curve are obtained by empirical experimentation in the field, and is the reference. But the problem to use this information, this index in a day-to-day basis, is the calculation, because well, it's not necessary to pay much attention to the equation. There are some only to demonstrate the complexity of the calculation, you know. But to calculate this index is necessary to know the amount of nitrogen per square meter or per hectare, and the amount of biomass. Obviously, in the past, in a experimental field, you can take a sample, a destructive sample, putting the crop, sending to the laboratory, and to obtain this data. But when you achieve this data, it's too late to manage the crop, so it's not operational. Thanks to the remote sensing, there are different parameters like chlorophyll index that allow to calculate this amount of nitrogen per square meter or per hectare, and also using model and different information coming from the remote sensing, is possible to calculate the biomass. So this index became operational thanks to the information. Thanks to the information coming from remote sensing. There are a lot of different indices related with the nitrogen or the chlorophyll to estimate the the amount of nitrogen per square meter or per hectare. For cereal, this is an example. For cereal, we use the Meris terrestrial chlorophyll index that perform very well in this kind of crops. Again, the importance of this information is to be available in a specialized way and easy to access and to consult, to query about the information. Not only to have maps or images like this representing different values of this chlorophyll index, but also the possibility to see the time evolution, the time evolution of the index for the same point, for the same peaks. Okay. The second question is what is one of the main contribution of remote sensing to nitrogen management? As I said, the main contribution is to allow to use this index in an operational way. If we consider the nitrogen nutrition index in an easy way to explain, is the comparison between the current nitrogen concentration of the crop in the moment that the image is taken, comparing with the critical nitrogen described in the curve as the curve I showed before. This is a simple equation, and we obtain values about 1, above 1 or below 1. And with this simple criteria, we can say if the nitrogen content in this moment in the crop is enough, there is a deficit, or there is an excess. It's important to remark that this index is calculated for every crop, depend on the crop, because the referent curve, the referent dilution curve that represent the nitrogen concentration in the tissue of the crop, obviously depend on the crop. Here you have an example of AgriSat with his platform, when you can see the image of the NNA distribution in the space, and also the evolution of the different points marked, different pixel marked in the image along the time. So the red point has enough nitrogen along the crop cycle, and the green point clearly is an area with deficit of nitrogen. For different reasons, it's necessary to go to the field to unravel what is the origin of this problem. But at the end, you have the information to analyze and to evaluate your management. Finally, I would like to show you a couple of real-life examples with the same crop. In this case, it's wheat, high protein and high yield wheat. Here you add the image, different image along the time, along the crops, the crop season, and you can see how only the image of the middle of this diagram has a right value, 1 or above 1. You can see for the color in comparing with the legend. So during this season, at the beginning of the crop, the crop suffer a deficit of nitrogen, and also at the end of the crop. That means less protein and less yield. Obviously, since this information is available almost on real time, one or two day delay from the acquisition, from the imagen acquisition by the satellite, it's possible to take action when you have the image. In this case, it's clear that the farmer would have been take a corrective measure, applying another top dressing, nitrogen top dressing, to avoid this long period of nitrogen deficit. In contrast, this is the same crop, the same variety, the same growing season, but you can see that this wheat, this plot of wheat, has not suffered a deficit of nitrogen, because all you can see in the figure, for every date we have a nitrogen index map. You can say that the color represent values 1 or above 1. So in this case, the nitrogen management has been correct, and is logically is expected the maximum yield and the maximum quality in expresses in protein content, because the crops has been supplied properly with the nitrogen all along all the crop season. And this is thank you for your attention. This is a real example of how with very complex equation, very complex scientific knowledge can be bringing to the farmer in an easy way and very intuitive way to manage. Thank you.
Thank you very much, Vicente. Thank you very much, Maria. Now we are going to move to the third and last part of this workshop before the questions. That is how we use these technologies, these remote sensing and WebGIS technologies in the B-FERST project. I want to remind that this project tries to create a brand new line of new fertilizers. So obviously all these technologies are focused on the management of the trials and the behavior of the crop and the fertilizers within the trial. Okay. So we're going to show you a practical application of these technologies and how we manage them in the B-FERST project. First of all is how we use these technologies for the field trial design. We start making an MCM, management zone map, of those plots that could be nice for the trial. So we have to analyze the different behavior, the different variability that we have in each part of the plots that we are going to scout. In example, this is the Poland pilot zone, and we want to do the trial this year in this part of the plot. So we can see, we can amplify in this case, the management zone map for this plot, we can see that there are different behavior. There's a different variability. It's very heterogeneous, the plot in this case. But watching this behavior, we can select, we can center our trial in this zone, because we have both high production and low production, or low productivity in this case part. So we have to select this part of the plot and then allocate each treatment depending on if it is on a high productivity or low productivity zone. After that, we use these remote sensing technologies and WebGIS for crop monitoring. We talked in the last presentations about the remote sensing parameters that we can obtain. For this project, we obtained obviously the NDVI in order to know the crop behavior. We also have information about the reference evapotranspiration, in this case not forecast, in this case just observed ETO. Because we calculate the transpiration using the NDVI. I remember that it is a linear relationship between NDVI and basal coefficient and the ETO in order to obtain the transpiration for each date that we have image from the satellite or the drone. And then there is a linear relationship between the transpiration and the biomass. So we can obtain the accumulated biomass from the beginning to the end of the cycle of the crop. Depending on the remote sensing source, we can use drones or we can use satellite images. In this case, we are using Sentinel-2, that is a constellation of the Copernicus European program. So in this case, we obtain these parameters in order to know the crop behavior and to obtain the biomass, and we can obtain from the biomass the final yield of the crop. And also, as Vicente have present before, there is a relationship between the content, the nitrogen content on the Greek cover, and the biomass. We obtain this nitrogen content directly from the chlorophyll index. That could be MTCI from Sentinel-2, or as an alternative when we use drone with other chlorophyll index, that in this case is read edge chlorophyll index. So with both parameters, we can correlate them depending on the crop, because this nitrogen nutrition index is crop dependent, to obtain the behavior of the nitrogen throughout the crop process and the crop cycle. And after that, we store, we upload all the information, all the images, and all the information of meteorological data, all the parameters that we need in our WebGIS platform in order to have at every moment in every place possibility to query for this behavior, to query for each parameter within each subplot, within each treatment and repetition. Okay, we can move to do a demonstration how we use our WebGIS platform. In this case, here we are, the Spanish field trial. this is the trial of the last campaign, 2021. We do this trial in parallel in Italy, in the same crop, but with different treatments. We also repeat this trial in Spain and Italy, but for this season, the crop changed to wheat. And we are going to start in commercial plots, because these plots are very small. So we have to use drone source for remote sensing. But in the other countries that are Poland and Portugal, and also we have to repeat in Poland due to the war in Ukraine, because there was a pilot zone in Ukraine, in Gerson. You can know about this, because in news there is a city that is with great damages due to the war. We have there our pilot zone, but we have to move to Poland in order to do the 5 trial for this year. These trials are in commercial plots. The size of these plots are 4 meters to 10 meters in Spain and Italy, micro plots in this case. And for the commercial trials, will be 40 by 40 square meters, 1,600 square meters each subplot. So we do 4 repetitions. So we have to prepare 4 blocks, 1, 2, 3, 4, and then we have, depending on the trial, controls. One is the white control without background fertilization. And we have also 3 controls. One is 100% of the mineral, conventional mineral fertilizer. The other is using the same conventional mineral fertilizer, but in this case, reducing the background fertilization dose to the 75%. And also in this case, for the organomineral control, using again 75% of needs. And we also do the same, the 75% of need for each new treatment. Okay, so in this case we have the vector layer with the spatial distribution of each trial, each subplot, each treatment and repetition. And we can move, example, to Italy in this case to see the other trial, last year trial. Going back to Spain, we derive directly from remote sensing, using in this case multispectral cameras, just in drones. We can derive different products as the RGB, natural color, just like a photo, and derive different indexes. An example, NDVI, and also for the nitrogen behavior, instead of merest terrestrial chlorophyll index, MTCI, that we use with satellite imagery, we use in this case grid edge chlorophyll index. That is another is an alternative for this type of source using drones. So we can check the information for each pixel. We first of all have to select, in this case, the period that we want to query. Here we have established the period for the previous campaign, from the 1st of May to the end of 2021, because the crop was corn. So So we can have the possibility to check from each pixel the behavior of each parameter, in this case, the NDVI value, and also the behavior of the chlorophyll index. Sorry, we have to check. As you can see, as much parameters we introduce in the temporal evolution query, we have different axes for each parameter. And then we use different GIS functionalities in order to obtain from each subplot, each treatment and repetition, the average value for each date of each parameter. We previously do a buffer, an internal buffer, in order not to avoid the possibility of confusion or confusing pixels that we have in the edge of each parcel. So we do an internal buffer about 2 meters in this case. And then we do the zonal statistic GIS functionality in order to obtain the average for each subplot, each treatment and repetition, and then to compare the values of each parameter graphically and using tables, just to obtain the behavior of each treatment in each trial. This is more or less an example of how we use this platform, how we use these remote sensing technologies. So going back to the webinar, now is the time to answer your questions. You have any question that you want to pose? You can use the chat to do the questions.
Anyway, our emails are available for any further comment or question.
Mm-hmm. So you have no questions. We close the workshop. Thank you for your attention, and we hope that it will be useful for you to understand how these technologies can be applied for the day-by-day management of crops. Thank you very much.